Howdy, folks. We are going to look today at the fundamental theorem of calculus, particle motion, and average value.
Three things to always keep in mind. So the first one is that when we integrate velocity, that we're doing it's really the difference of the positions. It's the change in position. So the integral of velocity is displacement or change in position. Sorry about that. So we are going to think about that quite a bit. When you integrate a rate, you just get a value of some other function. I'll call it the primitive function or the antiderivative. In this case, we know the antiderivative of velocity is position. Also, that the integral of velocity is the net distance. Because we're doing the PB minus the PA. That is the change in position, or again the displacement. But we're going to call that the net distance. Okay, so that's important. That's the net. Oh, I gotta charge the pen as usual. Let me pause this. So that's the net distance, because remember, net is the position, starting position minus final position, or in this case we're doing final minus starting position, so we don't have to do the absolute value guy. So that's our net distance. That integral represents our net distance or our net displacement. And if the velocity is always above zero, then this also represents the total distance whenever our velocity is always positive. The last thing is that the total distance can be calculated by the absolute value, the integral of the absolute value of velocity, because that'll take any negative parts and make them positive. So let's say, like, for instance, on A to B, if this was our velocity function, maybe it does something like this, if that's V of t. When we want to do total distance, right, our net distance here looks like it might just about be zero, maybe a little bit negative. Sorry, let's just talk about total distance. I don't want to confuse these two things. So our total distance, that means if we do the absolute value, it takes this part here that's below, and this function is the absolute. Maybe I'll do it in a different color. In red, this function is the absolute value of the velocity. And that'll take any negative parts and make them positive. So when we calculate that integral, it'll find all these areas as positive quantities and add them all together. So that'll get us our total distance. So whenever they're asking for total distance, regardless, even if you know the velocity function is always above the axis anyway, when we're doing total distance, let's just do the absolute value. Do the integral of the absolute value, just to be safe when you're given velocity. All right, so let's look at an example here. The velocity of a particle is moving along x is given by the function v of t. So we're going to do this without our calculator. So if the position of the particle at time 4 is 72, what's the position when t equals 2? All right, so we're going to calculate the integral from 2 to 4 of the velocity function. And we know that that's going to be equal to the position function 4 minus the position function at 2. Why did we choose the 2 and the 4? Because those are sort of the time values they give us. Okay, so now what's going to happen is we're going to say from 2 to 4, I'm going to write this a little bit. Let me zoom in a little so I have more room. From 2 to 4, we're going to substitute the function in here for velocity that we have. So it's 3t squared plus 6 dt. And that's going to be equal to 72 minus p of 2. All right, so we can now find the position when time equals 2. And again, there's multiple ways to think about this, but we're going to start with this way. So when I integrate, I get t to the third plus 6t, and we're going from 2 to 4, we're evaluating, and that's going to be equal to 72 minus the position at time 2. So I'm going to get 4 cubed plus 6 times 4 minus 2 cubed plus 6 times 2. That's going to be equal to 72 minus position at 2. So from here, we simplify this number, and we end up getting, and then we subtract 72, we're going to get negative p of 2 after we subtract 72 off both sides equals negative 4. So we got p of 2 equals 4. Again, I may talk about an alternative way to do this in class. So we can just kind of talk about that in person. For now, I kind of like doing it this way. Keeps it a little more algebraic. There is an understanding why we could do it maybe a little more intuitively, but I'm going to save that not for the video. What's the total distance the particle travels on the interval 0 to 7? So our total distance is going to be the integral from 0 to 7 of 3t squared plus 6 dt. Now, I know that this function is always positive, so this would be our total distance because of like 2 when we said it also represents the total distance. But if you wanted to be safe, you could absolute value it. Okay? This is a non-calculator question, so the absolute value is not going to be very helpful. But we know that it's always above the x-axis because it's a parabola that opens upwards and it's shifted up 6. So we're going to integrate. And plug in our 7. Plug in our 0. We get 385. So that is our total distance that the particle travels on that interval. Okay, now we're going to look at a calculator active question. So this time we're given a velocity function, and they give us a position at 1.5, and they want to know what's the position at 3.5. So if we integrate from 1.5 to 3.5, it's 0.5 e to the t times t minus 2 cubed dt. We can't do power rule on this. I mean, this will be a tough integral for us to calculate. So luckily it's a calculator active question, so we can say that integral, we know that since it's the velocity function, that'll be equal to the position, because the integral velocity is position. So the position of 3.5 minus the position of 1.5. And we know, so we'll do this integral on our calculator with fn integrate, or fn int. And we know that value is going to come out to be 15.919. And then p of 3.5 minus p of 1.5 was 2.551. So if we solve for p of 3.5, we end up getting 18.470. All right. What's the total distance the object travels from 1 to 5? Total distance, now just to be safe, I don't know if this function's above all the time or not, so we're going to do the absolute value of the function. For total distance, if we do the absolute value, that takes all our negative pieces and bounces them up into the positive area, positive region above the x-axis. So that's going to be the safe way to do total distance on our calculator. So our total displacement there, or I should say total distance, is that. All right, moving along. So you can pause and read the question. All right, so we're given a graph of the velocity, and we want to know what's the position of the particle at time 3. So it's going to be helpful to do the integral, since we have a velocity and we want to know about position. If we integrate velocity, we get position. So if we think of the integral of velocity, we can go from 3 to 8 of our velocity function. Again, let me do this. I need a little more room. From 3 to 8 of our velocity function. Why did I choose those numbers? 3 because they're asking me about what the position is at 3. 8 because they tell me the position at 8. So we know that when we integrate velocity, we'll do the position. That would be the position at 8 minus the position at 3. So we can figure out that integral from 3 to 8 based on our picture. We can do these are all geometric shapes that we can calculate. So if we go from 3 to 8, we've got this trapezoid here, and that'll be counted as a positive value. Then we've got this triangle that'll be counted as a negative value. So you can pause the video here and do that. See if you can come up with what that number is. Okay, welcome back. So you should have gotten 8 equals, and then P of 8 was 12. The position at 8 was 12 minus P of 3. So if I add P of 3 to both sides, subtract 8, I get P of 3 equals 4. And if I'm going for units, it's feet. How did I know that it was feet? Because the velocity was given in feet per second. So remember that when you integrate a rate, you get just a value. You get just a dimension, a distance. So that rhymes when you integrate a rate. So let's check out, what is the acceleration when t equals 5? Well, acceleration at time 5 is the same thing as the derivative of velocity at 5. So if we look on the graph here, at 5, it's on this downward sloping line. So I can find the average velocity, or the slope of that line, and it'll also be the instantaneous velocity there because it's the same, the velocity is constant. So it's going to be, 5 minus 0 over 4 minus 6. So we end up getting negative 5 halves. And that's going to be in feet per second squared because it's a rate of change of a rate of change. What is the net distance the particle travels from 0 to 10? So for net distance, that means we want to keep everything positive, so even negative areas will be counted. So since we have a picture here, a graph from 0 to 10, we're going to find this area, and it'll be a positive area, and we're going to add to it this area, and that would give us our net, so we're doing net distance, not total, I'm very sorry. So we will calculate this as negative area. Our net distance will have the negatives where they count. So if it were total distance, that's the one where I would want to count this area here, this yellow area, as positive area. But it's not, it's net distance. So we're going to calculate the positives as positives and the negatives as negatives. So the integral from 0 to 10 of the velocity of dt would give us our net distance, and we can find that by doing our geometric formulas. So you're going to do both of those areas, and again, we're going to subtract that lower piece. You can pause the video here and do that. Okay, welcome back. So you're going to get 20 minus 4. You should have got 16, and we are talking about feet because, again, we're integrating velocity. So velocity is a rate. We integrate a rate. We get just feet. What's the total distance? So here's the one where we're going to do the same thing as before, but instead we're going to add. So the total distance would be the absolute value of the integral. And you already calculated those areas. We had 20 minus 4. Well, now it's going to be 20 plus 4. So it's going to be 24 feet is the total distance. All right. All right, is this our last one? Oh, and then we got to do an AP question. Okay, so the table above shows the values of velocity. You can read this yourself. So what does the value of 0 to 18 velocity, of the integral from 0 to 18 of velocity represent? That would represent the net distance. So we'll say 0 to 18 velocity represents the net distance the particle travels from time 0 to time 18. Also notice that since all these values are positive, all the velocities are positive, that would also represent the total distance. So using a left Riemann sum of 6 subintervals of equal length, estimate the value. So we need 6. There's 1, 2, 3, 4, 5, 6. We want to estimate the value. These are all equal length because they go up by 3 every time. So that's nice. That means I could factor them out. So from 0 to 18, that area under the curve can be approximated by the width of each rectangle is 3. Now I got to do the heights of each one. So we're doing left-hand Riemann sums. So that means we're going to use all of these left values. That's the left of each interval. And we don't use the rightmost one, right? So it's going to be 2.3 plus 2.7 plus 2.0 plus 1.3 plus 1.0 plus 1.7, and it's that number which will work out to be about 33 meters, or exactly 33 meters. They wanted to use units of measure. Remember that this was in meters per second. We're integrating a rate, so when you integrate a rate, you get just the value meters. If it's meters per second, we get just meters. Using a right Riemann sum of 6 subintervals of equal length, estimate the value from 0 to 18. So 0 to 18. So now we're going to do a right Riemann sum. So the widths of all of the rectangles are still 3. But now since we're doing a right-hand sum, we don't use the leftmost height. Our first rectangle will have the height on the right side of its rectangle, which is, so we're going to go 2.7 plus 2.0, plus 1.3 plus 1.0 plus 1.7 plus the last one, which is 2.1. All right, so that's going to work out to be 32.4 meters. Now we're going to do a midpoint Riemann sum of 3 subintervals. So this one's nice. They actually are midpoints. So we're doing 3 intervals. So we'll do 1, 2, and 3. And this is the height of the midpoint for each interval. So again, midpoints are still rectangles. So from 0 to 18 can be approximated as, now the width of these rectangles are now 6 units long, times each height, and that's the height of the midpoint, so it's going to be 2.7 plus 1.3 plus 1.7. That's going to work out to be 34.2 meters. These are all different approximations of the same area under the curve. Now we're going to use a trapezoidal sum of 6 subintervals of equal length. So for trapezoids, we're going to go 1/2, and then the height of the trapezoid is 3, and we can factor that out of each term. So now we just need all the bases. So the first base is 2.3 plus 2.7 counts. Remember, this is the length of the base of the first trapezoid and also the length of the base of a second trapezoid. So it's going to be 2 times 2.7 plus 2, and that happens each time until we get to the last one. So that number is going to be about 32.7 meters. That's our approximation doing trapezoidals. And they want us to find the average acceleration of the particle from 3 to 9. For what value of t on the table is this average acceleration approximately equal to v prime of t? Explain your reasoning. All right, so the average acceleration for the particle from 3 to 9. So remember, we've got velocity here. So if we do the average rate of change of velocity, right, that means the change in velocity divided by the change in time. If we do that average rate of change of velocity, that's really the average acceleration. Rate of change of velocity is also known as acceleration. From 3 to 9. Whoops. So we're using 3. We're doing the average from 3 to 9. So our average acceleration from 3 to 9 will be the velocity of 3 minus the velocity of 9. 3 minus 9. That's going to be 2.7 minus 1.3 all over negative 6. It's equal to negative 0.233 meters per second squared. So then what they want us to do for what value of t in the table is the average acceleration approximately equal to v prime of t. What did we get here? Negative 2.2. So, all right. So what we're going to do here is we're going to say according to the mean value theorem, this average acceleration should be approximately equal to v prime of 6. And that's because of they say that we know that there is mean value theorem guarantees that there's a c between 3 and 9, right? For which v prime of 6 or acceleration is equal to that. So there is some c. The reason we said 6 is because it says for what value of t in the table. So we really only have one choice. There's only one value that's in between 3 and 9, so that's why we're able to say that. This is kind of it's not a great, I don't know if I really want to say according to the MVT, but I have because I know there's one in between, and I would be just as fine as if you said you didn't use MVT, but you said something about the slope of the secant line being a good approximation for the derivative. That's fine as well. I really kind of like that also. All right, let's do this FRQ so we can be done with today's notes. All right, so we've got a graph here of acceleration. So cars traveling on a straight road. You can read it. I'm not going to read it to you. All right, so let's take a look at what we need to do here. Is the velocity of the car increasing at t equals 2 seconds? Why or why not? So for A, we're going to say that at t equals 2, the acceleration is 15. So since, we'll say since acceleration at 2, which is equal to the derivative of velocity at 2, is 15, which is positive. So we can say all of that, right? Our acceleration is positive. Then we know the velocity is increasing at t equals 2. All right, B, at what time in the interval other than t equals 0 is the velocity of the car 55 feet per second and y? So remember, it starts out with a velocity of 55 feet per second at time 0. So when does it return back to that velocity? So here's the part where we've been doing a lot talking about the connection between velocity. If I'm given the velocity graph, that I can talk about the position, and that the area under the curve is talking about positions, net positions and distances. Well, now the area under the curve is going to be a velocity, right? Because we have acceleration, so area under the curve steps it back one function, so it's going to take the antiderivative of acceleration and be velocity. So the area under the curve here is all positive up until this point. And if we want to arrive back at our original velocity that we started at, we need to cancel out all that velocity, all that positive velocity with some negative velocity. So at what point do we cancel it out and get back to a net velocity of 0? That's the way to think about it. Because this is acceleration, instead of distance now, we're talking about velocity or change in velocity. Our net change in velocity is what I should say. Our net change in velocity here is 0 because I've got equal parts above and below. So that's sort of how you want to think about that. So we can say at time at t equals 12, and we could say that's because the integral from 0, let's say it this way, because the integral from 0 to 12 of acceleration, that could be equal to velocity of 12 minus velocity at 0 is equal to 0. So that shows that whatever my initial velocity was, right, my velocity at 12 has to be the same thing for those when I subtract them to equal 0. So that's one way you could kind of say that. All right, let's look at part C. On the time interval 0 to 18, what's the car's absolute maximum velocity in feet per second? And at what time does it occur? Justify your answer. So now we're looking for an extreme value here. So the extreme value theorem says that the absolute maximum will occur at the endpoints of the interval or anywhere the derivative, so we're talking about maximum velocity, so the derivative of velocity, which is equal to acceleration, is equal to 0, right? That's what the extreme value theorem says, that you check the intervals and anywhere where the function or the thing you're trying to find the maximum of, wherever its derivative equals 0 or undefined. All right, so that means our endpoints are at, we want to check the velocity at 0. We want to check the velocity, what's the interval? Yeah, 0 to 18. We want to check the velocity at 18 and the velocity at 6. Okay, well, we know our initial velocity at 0, they gave it to us in the problem, right? It's 55 feet per second. now we need our velocities, and we want the absolute maximum. Velocity of 18 will be out because if we look at, well, let's do velocity of 6 first, actually, I think is helpful. Let's figure out the velocity of 6. So how do we figure out a velocity at a point when we don't have the velocity graph or the velocity function? Remember, we're going to say the velocity, we can say, well, we'll say the integral from 0 to 6. Why do we choose those? Because I have times 0, I have the velocity at 0, and I'm looking for the velocity of 6 of the acceleration function can be equal to the velocity of 6 minus the velocity of 0. And we can solve this for the velocity of 6, which is what we're looking for. So first I can get the integral from 0 to 6 from my graph. That shape is a trapezoid. So it's got a height of 15. It's got base lengths of 6 and 2. So it's going to be 1/2 times 15 times, sorry, 2 plus 6. And that's going to be equal to V of 6 minus V sub 0 was 55. Or V of 0, I should say, was 55. Geez, I got to fit a part D in here, huh? Let me make this a little smaller. So when I solve this thing, I'll get V of 6 equals, let's see here, we got 8, 4, 15 times 4 is what, 60? 55? Because we've got, well, give me a second, sorry, 8, 4. 4 times 15 is, yeah. So we're going to do the 60, and then we're going to add our 55 to get our V of 6. So we're going to get 115 for V of 6. So it's 115 feet per second. And that was for V of 6. Now for V of 18, we can do something similar to what we just did. And there's a couple other ways. There's like a faster way to do it as well. So let's do V of 18. So I'll do that over here to save some room. So V of 18, the way we figure that out, again, let's do our integral. So there's a couple ways to do this. What we're going to look at is we now know V of 6, right? So we can use V, we can start at 6 because we know what V of 6 is. If I integrate this from 6, the acceleration, to 18, I'm going to have a negative net acceleration there. So I'll have negative, negative net velocity. So we're going to write out, I lost my place here. Where was it? Did I just lose a bunch of stuff? No, okay. So we're going to go our integral from 6 to 18 of our acceleration function. That's going to be equal to V of 18 minus V of 6. And we know that what V of 6 is. So now we're going to say from 6 to 18 acceleration dt equals V of 18 minus 115. Now here's the trick. We didn't calculate. You could calculate the area. We didn't. It's enough to know that that area is negative. So what does that mean about V of 18? V of 18 must be larger smaller than 115. V of 18 is smaller than 115. Or we could say V of 18 is less than V of 6. So that means that V of 6 must be the maximum, and so the absolute maximum velocity. So we're going to answer the question, the absolute maximum velocity is 115 feet per second. Let me make sure I answered what they wanted. Did they say what is? On the timer, what is the car's absolute maximum velocity and what time does it occur? Which occurs at t equals 6 seconds. Okay, so since we knew, I just want to come back here, since we knew that this value was negative, that's why we know that to get a negative, this number has to be smaller than the second number because we're subtracting. Okay, and let's look at, did I leave enough room? Hopefully. Let's look at the last part, part D. At what times in the interval 0 to 18, if any, is the car's velocity equal to 0? Justify your answer. Okay, so at what times, if any, is the car velocity equal to 0? Justify your answer. So I think they're trying to trick us into saying that like before what we kind of said, that these cancel out, so therefore the velocity is 0. Remember, when you're finding the area under the curve, it's the net change in the velocity. It's not what the velocity is. It's what it's changed. So you could say, like, I could say your bank account has changed by me adding $100 to it. That doesn't mean you have $100. That's what it changed by. You would have to know how much you started with. Or we can use our little thing where we solve our integral to figure out the amount. So I'm going to start by saying that we want to find the absolute minimum, possibly, is how we want to look at this, you could say, of our velocity. So that's going to occur when, look, we start off with a velocity and its net change is positive, 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 positive. So the velocity is just growing, increasing, right? It's increasing. And then when we switch to negative, the net is still positive, but it's getting less and less because all this negative area is canceling it out until we get to a net change of 0 right here. So it doesn't mean that our velocity is 0. It just means we're back at 55 feet per second because our net change in velocity is 0. Now, anywhere after 12, it starts getting into the negative because now our net change is negative. So now our velocity is going to start dropping below 55. So now we could be approaching our minimum, and it's going to keep going down until we get to 16. Then we start adding positive change in velocity back on. So it's going to start, the velocity is going to start going back up again. All right, so that tells us that the only place it could possibly, where the velocity could get to 0 is where it's going down. So it's in between 12 and 16. That's the part where we finally got to a net change in velocity of 0. And it keeps going down. So then the lowest point, the lowest velocity, the absolute lowest velocity will be at 16. So can we just calculate what the velocity at 16 is? So to do that, we would do the integral of, since we don't have a velocity function, right? We could do the integral of acceleration. And we want to include 16 for sure. And we know what v of 6 is, so we'll use v of 6. So if we go from 6 to 16, we know that integral can be computed as the velocity of 16 minus the velocity of 6. And this way we can figure out what the velocity of 16 is. Another way to think about this is, well, let's finish this way, then I'll talk about that. So we need to calculate the area from 6 to 16, which is a trapezoid here. And so from 6 to 16, we've got our bases on our trapezoid is 10. And then this guy goes from 10 to 14 is 4. And then the height is 15 here. Okay, so we're going to calculate that trapezoid, and then we're going to see and solve this integral for v of 16. So it's going to be 1/2 times, the bases were 10 plus 4, I think we said, times the height, it was a negative 15 because it went down 15. That's going to be equal to v of 16 minus, we knew v of 6 is 115. So what we're going to do is look at this area here. We figure that out. 7 times negative, because we got 14 times 1/2 is 7 times negative 15 is going to be negative 105. Remember what that means now. That is the net change in velocity. We can start thinking about this as an accumulation function, so we don't always have to do this to find a value of v of 16 or v of 6 like we did earlier. What we can do is, instead of writing it how we have it here, and we've talked about this in class at this point hopefully, we can say it's v of 6, the value we know, plus the net change. So it's kind of where we started plus how much it changed. Right, so this is an alternate way. We could start from here. So we could say it's v of 6 plus that negative 105. So whatever the velocity was at time 6 is going to have a net change of 105 by the time it gets to 16. So that's another way to think about it. All we really did was we took and added that initial time over here. Now the thing is, you add it if you're moving left to right. So we think of this as an accumulation, is what we say. If we started at 6, we know whatever the velocity is. As we're moving left to right, that means we're going to be adding it on. If we move right to left, it's going to be subtraction. We'll talk about that if we haven't already. So this is an alternate way to look at it. Either way, we're doing v of 16, right, equals, that's what v of 16 is equal to, v of 6, which was 115 minus 105. So we end up getting 10. That is our lowest possible velocity. And so no, the velocity will never get to 0. Sorry this is taking so long, but I'm trying to kind of show you two different ways. This is what we start to talk about when we say accumulation, thinking of the integral as an accumulation function. Here we're still just sort of straight using the fundamental theorem of calculus and then solving to find v of 16. So in here, right, we would add 115 to both sides, and we're still at our v of 16 equals 10. And that's going to be the lowest our velocity gets to, which we said before. So it could never equal 0. So the car's velocity is never equal to 0. And we can say that because we showed like v of 16 is 10, which is bigger than 0, and v of 16 is the absolute minimum. We could even talk about, I don't think we need to because we sort of talked about extreme value theorem above a little bit. We used it to compare all of those. That was to find the extreme maximum. The minimum will occur at that v of 16. I think we're done. Yeah, we're done.